At the beginning of this video, I explained to you that I will explain some complex enthalpy standard enthalpy changes. So the first standard enthalpy, one of the complex changes is the atomization. So atomization is not complex, but in some cases you may find it complex. So atomization is somewhat similar to the bond dissociation in that we actually break up bonds. So atomization involves steps in which we break up some molecule into its element form or the atom form, right? So we break up into one mole of an element. So the standard enthalpy of atomization for some compound or the reaction is defined as the change in enthalpy that takes place when a mole of an element under the standard conditions is converted into a mole of atom in the gaseous state. So you may have seen here that for example, if you take chlorine, you take half a mole of chlorine and then you convert it to one chlorine element here. So the energy required for such a reaction has been found as 121 kilojoules per mole. Similarly, you can take iodine here, you can convert iodine in its solid state into iodine into gaseous state. So you know that iodine is actually in the solid state unlike chlorine under standard conditions, because we take standard conditions here, so we have to take iodine in the solid format. So iodine in the solid format has to be converted into iodine into gas format using two steps, because this is in the solid format and we have to convert it to gaseous format. So first of all, you need to convert this into a gaseous format. As in the case here, you should have a gas into a gas here. So what we do is we first of all convert this solid into a gas using using the standard enthalpy of sublimation. So when I2 is converted to I2 gas, it is the standard enthalpy of sublimation. Since the coefficients here are half and half, we actually have to halve the total energy or the standard enthalpy of sublimation. So we take half of the delta H is phi here. Then what we have to do, as in the case of chlorine, is that we can find that this to be equal to half of delta HD here. So by Hess law we can say that delta HAT is equal to half times delta HS plus half times delta HD. So that's it about the standard enthalpy of atomization. And the next important enthalpy that I'll be talking about is the standard enthalpy of first ionization or delta HIE1. So first ionization, you know that when we have first ionization, you get the sodium gets converted to sodium plus and an electron is released. So you know that when you increase the energy, the electrons inside an atom vibrate with some frequency, and at some frequency, at actually the resonance frequency, it vibrates with the amplitude, or it goes to the maximum energy level or the infinite energy level that the electron can hold. So at that energy level, that electron gets freed from the nucleus attraction of that element, and that forms the first ionization of that element. So the energy required or the energy change required for such a reaction is defined as the standard enthalpy of first ionization. So it's defined as the change in enthalpy that takes place when a mole of a unipositive ion, so unipositive ions are sodium plus, potassium plus, and so on. Unipositive ions are formed under the standard conditions by removing an electron each that is most weakly bonded to the nucleus from a mole of gaseous atoms of an element. So you should take the most weakly bonded electron. So that is actually we also call the valence electron, that can be easily gifted and easily taken into the compound or into the element. So that is removed to form the positive or the cation of the positive ion, and the energy in the case of sodium has been found to be positive and 496 kilojoules per mole, because we give heat. This is an endothermic reaction. And the reverse reaction of standard enthalpy of first ionization is the standard enthalpy of electron affinity. In the case of enthalpy, as I mentioned, in the case of periodic table and the bonds, electron affinity is the reverse reaction of ionization. Ionization involves removing an electron. Electron affinity involves gaining an electron. So electron affinity is normally defined for non-metals or elements in the groups of 5, 6, 7 in the periodic table. For example, if you take chlorine as presented here, you do not remove an electron of chlorine, you provide an electron for chlorine, and that forms the chloride ion with the electron configuration of the argon gas. So the standard enthalpy of electron affinity is defined as the change in enthalpy that takes place when a mole of a uni-negative ion are formed in the gaseous state, and it should be in the gaseous state under the standard conditions when electrons are given to a mole of atom in the gaseous state. So the energy change of the standard enthalpy of electron affinity for chlorine has been determined or calculated to be minus 352 kilojoules per mole, and that's an exothermic reaction. So the next enthalpy that I will be talking here is about the standard lattice enthalpy of an ionic compound. So this is actually the most important enthalpy, because the standard lattice enthalpy of an ionic compound is a summarization of all the other enthalpies. So that you will find when I am explaining about the Born-Haber cycles. So the standard enthalpy of an ionic compound, although doesn't seems to be an important reaction, is actually the summarization of all these concepts, because to form the lattice you need all these reactions. So standard enthalpy of lattice enthalpy of an ionic compound. Now you know that to form an ionic compound you should have two ions, one a cation and an ion. So for example, if you take sodium and chlorine, the cation is the sodium plus ion, and the anion is the chlorine minus ion, or the chloride ion. So the sodium plus ion and the chloride ion form sodium chloride. So both of these are in the gaseous state and it forms a solid. So the energy for such a reaction has been found to be minus 780. So the energy is given out. It's an exothermic reaction, and it is defined as a change in enthalpy that takes place when 1 mole of an ionic compound in the solid state under the standard conditions are formed from gaseous positive ions and negative ions. So there are various factors that affect the standard lattice enthalpy, and this is explained using the general Madelung constant and the Madelung equation. So we call this delta H L as the standard enthalpy of lattice energy, L as the Avogadro constant, A as the Madelung constant. So that's a constant that depends upon the lattice or the standard the ionic compound, that depends upon the ionic compound. It's a constant. Avogadro constant is a constant for any ion or any element, or it's 6.022 times 10 to the power 23 per mole, but the Madelung constant varies depending upon the compound or the ionic compound that you making is as a subject. So Z1 and Z2 are the charges of the two ions making the bond. For example, if you take sodium and chlorine, Z1 is the charge in coulombs of sodium. So sodium is an unique positive ion, so its charge will be 1.602 times 10 to the power minus 19 and coulombs. And Z2 for chlorine is a negative ion, so that will be minus 1.062 times 10 to the power minus 19 coulombs. So E is the charge, and R is the ionic distance, and N is a constant that depends upon the electron configuration of the two ions. So if you want to calculate this, you need to know what are the values of A and N, and also R, the inter-ionic distance. So if you know those values, you can calculate the standard enthalpy. But for most of these values, the standard enthalpy is the expected value from such a calculation is different from the expected value from a practical example. For example, if you take sodium and chlorine here, what generally happens is that when you form sodium chloride from sodium and chlorine, this is minus 780 joules. But if you calculate it, it will be close but not equal almost for most of these compounds, because that requires some additional steps which I will not be explaining in this video. So what is important here is not about this difference, it's important here about some relationships. From the above equation, you can see that delta HL is inversely proportional to the inter-ionic distance. Thus, when small atoms make a certain lattice, the lattice energy for such a structure should be high. Thus, the stability for such a structure is also high. And another important relationship is that this standard enthalpy, lattice enthalpy, is directly proportional to the product of the charges of the two ions. So when the charges of the two ions increases, the standard enthalpy is high. For example, if you take magnesium chloride, the standard enthalpy of the standard lattice enthalpy for magnesium chloride should be high, because you take +2 of magnesium and -1, so that forms -2. So magnesium chloride is much strength, has a high strength. So you can also say that when the size of atoms decreases and when the magnitude of the charges increases, the standard lattice enthalpy for such a molecule increases. So that's it about the different types of standard enthalpy. So this is actually a theory part. So I'll explain you about some practical examples or some sample calculations in my next videos. So before explaining about the sample calculations, I need to explain you about the standard definitions. So that's the reason as to why I designed this video and the last two videos. So hope you gain some knowledge through these videos and the last two videos, and then I will explain you about some practical sample solutions to a practical problem that you will come across through these definitions of thermochemistry. So thanks for watching this video, and see you soon.